At the end of this video, you should be able to describe motion in terms of frame of reference, displacement, time, and velocity, calculate the displacement of an object traveling at a known velocity for a specific time interval, and construct and interpret graphs of position versus time. Chapter 2, Section 1, Displacement and Velocity Motion. Motion appears all around us. Every day we see objects such as cars, people, and soccer balls move in different directions with different speeds. In this chapter, we will discover how to analyze motion as a physicist does. One way to simplify the concept of motion is to consider only 4 kinds of motion that take place in one direction. As an example of this one-dimensional motion is the motion of a commuter train on a single track, like the one shown on the screen here. In this one-dimensional motion, the train can move either forward or backward along the tracks. It cannot move left and right or up or down. This chapter deals only with one-dimensional motion. In later chapters, you will learn how to describe more complicated motions, such as the motion of thrown baseballs or other projectiles. It seems simple to describe the motion of a train. As the train, again shown on the screen here, begins its route, it is at the first station. Later, it is at another station farther down the tracks. But Earth is spinning on its axis, so the train, the stations, and the tracks are also moving around the axis. At the same time, Earth is moving around the Sun, and the Sun and the rest of the solar system are moving through our galaxy. And this galaxy is traveling through space as well. When faced with a complex situation like this, the physicist must break down the situation into simpler parts. One key approach is to choose a frame of reference against which you can measure changes in position. In the case of the train, any of the stations along its route could serve as a convenient frame of reference. When you select a frame of reference, note that it remains fixed for the problem in question and has an origin or starting point from which the motion is measured. If an object is at rest, meaning not moving, its position does not change with respect to a fixed frame of reference. For example, the benches on the platform of one subway station never move down the track to another station. In physics, any frame of reference can be chosen as long as it is used consistently. If you are consistent, you will get the same results, no matter which frame of reference you choose. But some frames of reference can make explaining things easier than other frames of reference. For example, when considering the motion of the gecko shown on the screen here, it is useful to imagine a stick marked in centimeters placed under the gecko's feet to determine the frame of reference. The measuring stick serves as an x-axis. You can use it to identify the gecko's initial position and its final position.
A train moves from one station to another, on an Earth that is rotating and revolving and in a solar system and galaxy that are both moving. A frame of reference is defined to simplify the description of the train's motion. The motion of this gecko can be described by imagining a meter stick placed under the gecko to define a frame of reference. Observers in different frames of references will see the motion of objects differently. The red dot in this picture is a stunt dummy dropped from the plane. From an observer in the frame of reference of the moving plane, the dummy appears to drop straight down and splash in the water. And from an observer in a stationary frame of reference on the ground, the dummy appears to fall in a curved path.
As any object moves from one position to another, the length of the straight line drawn from its initial position to the object's final position is called the displacement of the object. The gecko, again shown on the screen here, moves from left to right along the x-axis from an initial position, x sub I, to a final position, x sub f. The gecko's displacement is the difference between its final and initial coordinates, x sub f minus x sub I. In this case, the displacement is about 61 centimeters, which is 85 centimeters minus 24 centimeters. The Greek letter delta, represented by a triangle before the x, denotes a change in the position of an object. Now suppose the gecko runs up a tree, like the one shown on the screen here. In this case, we place the measuring stick parallel to the tree. The measuring stick can serve as the y-axis of our coordinate system. The gecko's initial and final positions are indicated by y sub I and y sub f, respectively, and the gecko's displacement is denoted as y. Displacement does not always tell you the distance an object has moved, however. For example, what if the gecko, again shown on the screen here, runs up the tree from the 20 centimeter marker, right, meaning its initial position, and it runs to the 80 centimeter marker. But after that, it retreats back down the tree to the 50 centimeter marker, which would be its final position. It has traveled a total distance of 90 centimeters. However, its displacement is 30 centimeters, because the difference between the final y position and the initial y position, remember that's 50 centimeters minus 20 centimeters, is 30 centimeters. If the gecko were to return to its starting point, the displacement would be 0, because its initial position and final position would be the same.
As any object moves from one position to another, the length of the straight line drawn from its initial position to the object's final position is called the displacement of the object. Displacement equals change in position, or the final position minus initial position. If our ball travels from an initial position x equals 12 meters to a final position x equals 35 meters, the displacement is 23 meters. But what happens if the ball travels from the 35-meter mark to the 12-meter mark? If the ball travels from an initial position x equals 35 meters to a final position x equals 12 meters, the displacement is negative 23 meters. Keep in mind that the displacement is not necessarily the total distance covered. If the ball were rolling along from an initial position of 12 meters, hit a wall at 35 meters, and rolled back to a final position of 18 meters, the overall displacement is only 6 meters. When working with displacement, always look at the initial position and the final position of your object.
Displacement also includes a description of the direction of motion. In one-dimensional motion, there are only two directions in which an object can move, and these directions can be described as positive or negative. In this course, unless otherwise stated, the right, or east, will be considered the positive direction, and the left, or west, will be considered the negative direction. Similarly, upward, or north, will be considered positive, and downward, or south, will be considered negative. The figure on the screen here gives examples of determining displacements for a variety of situations. Where an object started and where it stopped does not completely describe the motion of the object. For example, the ground that you're standing on may move 8.0 centimeters to the left. This motion could take several years and be a sign of the normal slow movement of Earth's tectonic plates. If this motion takes place in just 1 second, however, you may be experiencing an earthquake or a landslide. Knowing the speed is important when evaluating motion. Consider the car on the screen here. The car is moving along a highway in a straight line. We'll call that the x-axis. Suppose that the positions of the car are x sub I at t sub I and x sub f at t sub f. In the time interval t, which is equal to t sub f minus t sub I, the displacement of the car is x, which is equal to x sub f minus x sub I. The average velocity, v sub average, is defined as the displacement divided by the time interval during which the displacement occurred. In SI, the unit of velocity is meters per second, abbreviated m over s. The average velocity of an object can be positive or negative, depending on the sign of the displacement. The time interval will always be positive, however. As an example, consider a car trip to a friend's house 370 kilometers to the west, the negative direction, along a straight highway. If you left your house at 10 a.m. and arrived at your friend's house at 3 p.m., your average velocity would be as shown on the screen here. Your value is an average. You probably did not travel exactly 74 kilometers per hour at every moment. You may have stopped to buy gas or have lunch. At other times, you may have traveled more slowly as a result of heavy traffic. To make up for such delays, when you were traveling slower than 74 kilometers per hour, you must also have had other times when you traveled faster than 74 kilometers per hour. The average velocity is equal to the constant velocity needed to cover the given displacement in a given time interval. In the example on the screen here, if you left your house and maintained a velocity of 74 kilometers per hour to the west at every moment, you would take 5.0 hours to travel 370 kilometers. At this point, you should be able to attempt sample problem A.
Suppose a car moves from point X sub I at time t sub I to point X sub f at time t sub f in the amount of time shown by the clock. The average velocity of the car is the displacement divided by the change in time. Since the car is traveling to the right, the sign of the displacement is positive and is equal to x sub f minus x sub I. The time interval is always positive and is equal to the final time minus the initial or starting time. The average velocity can be a positive or negative value because the displacement can be either a positive or negative value. Even though the motions of these two cars differ, at time t sub f they have the same average velocity because they underwent equal displacements in the same amount of time.
In everyday language, the terms speed and velocity are used interchangeably. In physics, however, there is an important distinction between these two terms. As we have seen, velocity describes motion with both a direction and a numerical value, meaning a magnitude, indicating how fast something moves. However, speed has no direction, only magnitude. An object's average speed is equal to the distance traveled divided by the time interval of the motion, which is to say, average speed is equal to distance traveled divided by the time interval. The velocity of an object can be determined if the object's position is known at specific times along its path. One way to determine this is to make a graph of the motion. The figure on the screen here represents such a graph. Notice that time is plotted on the horizontal axis and position is plotted on the vertical axis. The object moves 4.0 meters in the time interval between t is equal to 0 seconds and t is equal to 4.0 seconds. Likewise, the object moves an additional 4.0 meters in the time interval between t is equal to 4.0 seconds and t is equal to 8.0 seconds. From these data, we can see that the average velocity for each of these time intervals is positive 1.0 meters per second, because the average velocity is equal to the change in position divided by the change in time, which is to say 4.0 meters divided by 4.0 seconds. Because the average velocity does not change, the object is moving with a constant velocity of positive 1.0 meters per second, and its motion is represented by a straight line on the position time graph. For any position time graph, we can also know the average velocity by drawing a straight line between any 2 points on the graph. The slope of this line indicates the average velocity between the positions and times represented by these points. To better understand this concept, compare the equation of the slope of the line with the equation for the average velocity. We see that slope is equal to rise over run, which is equal to the change in vertical coordinates divided by the change in horizontal coordinates. The figure on the screen here represents straight line graphs of position versus time for 3 different objects. Object 1 has a constant positive velocity because its position increases uniformly with time. Thus, the slope of this line is positive. Object 2 has 0 velocity because its position does not change, meaning the object is at rest. Hence, the slope of this line is 0. Object 3 has a constant negative velocity because its position decreases with time. As a result, the slope of this line is negative. Now consider an object whose position versus time graph is not a straight line but a curve, like the one shown on the screen here. The object moves through larger and larger displacements as each second passes. Thus, its velocity increases with time. For example, between t is equal to 0 seconds and t is equal to 2.0 seconds, the object moves 8.0 meters and its average velocity in this time interval is 4.0 meters per second, because the average velocity is equal to 8.0 meters divided by 2.0 seconds. However, between t is equal to 0 seconds and t is equal to 4.0 seconds, it moves 32 meters, so its average velocity in this time interval is 8.0 meters per second, because average velocity is equal to 32 meters divided by 4.0 seconds. We obtain different average velocities depending on the time interval we choose. But how can we find the velocity at an instant of time? To determine the velocity at some instant, such as t is equal to 3.0 seconds, we study a small time interval near that instant. As the intervals become smaller and smaller, the average velocity over that interval approaches the exact velocity at t is equal to 3.0 seconds. This is called the instantaneous velocity. One way to determine the instantaneous velocity is to construct a straight line that is tangent to the position versus time graph at that instant. The slope of this tangent line is equal to the value of the instantaneous velocity at that point. For example, the instantaneous velocity for the object on the screen here at t is equal to 3.0 seconds is 12 meters per second. The table on the left side of the screen here lists the instantaneous velocities of the object described by the graph on the screen here. You can verify some of these values by measuring the slope of the curve.
The first thing you need when setting up a sign convention for velocity is a defined axis system, with time along the x-axis and displacement along the y-axis. For motion in one dimension, velocity is positive when the object moves in the positive direction on the defined axis system. Since the position value is increasing, the graph slopes upwards. Velocity is 0 when the displacement stays constant. In other words, the position value does not change. This line has 0 slope. Velocity is negative when the object moves in the negative direction on that axis system. This line has a negative slope.
At this point, you should be able to describe motion in terms of frame of reference, displacement, time, and velocity, calculate the displacement of an object traveling at a known velocity for a specific time interval, and construct and interpret graphs of position versus time.